Okay, I think we can start 1 minute before 10:30. Let's start with any.
Yeah, we can start. Yeah.
Okay, so we can start with any Q&A if there's any questions before we start the lecture today.
Any questions from audience?
Okay, if there's no question, great. Let's start our day 4 lecture. Today we will look into signal processing, particularly for the data inversion interpretation for early stage fatigue damage problem. We briefly discussed this in the introduction class, and we'll go into the details for this interesting problem. The second half, we already covered that yesterday as we discussed at today's afternoon lab session. It will, you'll have we'll have no lecture, and you have those 2 hours working on your project, and moderated by Professor Rao. But I do have our lab session material that I mentioned yesterday on the structuralized system. I hope that we can have time this morning to go over that. So that's option number 2 we had yesterday. So let's see if we have time. I just want to talk about more examples. So let's see. All right, so okay. So the material we're going to cover today, first we will go over the physics of magnetic background noise. I know this has not been covered in course number 1, so we'll go over the theory a little bit. Then we will talk about how we collect the data, then the basics of the data analysis for MBN. We'll talk about another method, and I'm sure this has not been covered, which is a nonlinear current. So we'll talk about the same thing, the theory, then the experimental setup, data acquisition, and analysis. And for this course, we'll focus on the data analysis in both time domain and frequency domain. We'll present some advances in fatigue, early stage fatigue damage assessment using PCA, PNN, and on-sodium quantification. Right. So with that, I will start the physics of MBN first. Magnetic background noise. So it has great potential, as we discussed before. It's one of the micromagnetic methods. And it has been there for decades. But still, there's a lot of work going on there, and also there are commercially available tools out there that you can use that to measure, for example, the surface residual stress, as well as microstructural parameters of the material. It has been used in several applications. For example, the carbon content characterization based on the signal features, and we'll talk about that more. And if you are interested in this, there are a lot of publications out there. And what we did at Michigan State before is we developed a system, and we can use the signal features to quantitatively assess the carbon content of a ferromagnetic material. You can also use that to correlate the background noise profile with the magnetic properties of steel. For the dual phase steel, you can use the ferrite grain size or martensite percentage to study the material properties of steel. The basics of this method can be explained using those 3 figures. The very left one just showing you the magnetic domains for ferromagnetic materials without external fields. So the magnetic moments within each domain kind of pointing to random directions. So overall, you won't have, um, you know, you know, a, a magnetic moment in one direction. But when you have this material exposed in the external magnetic fields, then the magnetic domain will be changing in a way that those magnetic moments will be aligned in the same direction of the external magnetic fields, excited by the AC. You can have an AC circuits to do that. So when you change that in a time varying pattern, then the pinning sites in the domain wall, due to the microstructure um, properties, that will lead to discontinuities and non-uniform changes in the magnetization and pickup by your sensor, which is like a noise type of signal. The representative ambient signal, when you have those periodic excitation, the signal will also look like periodic and something like this. Okay, so you can capture those signals, and you can actually use coin type of signals. I'm sorry, coin type of receivers to pick up the variations due to the magnetic changes in the magnetic domains. So this is the setup. We talk about the samples from EPRI, where we develop a system. We put the excitation magnetic circuit on the sample surface where we want to measure the changes in the microstructures. We excite the system using the excitation signal. Here we can use a sinusoid signal. Of course, you can use other type of excitation, and choose the peak-to-peak value and also the frequency accordingly based on the problem you're working on. Amplify the signal, acquire the signal, and perform the signal processing. The way to collect the data, as we mentioned, that we're trying to capture the microstructure changes in the material, and the spatial sampling on the sample is necessary, so we can have a more something like a raster scan image or data collection region of interest shown here. There are a total 18 points for this particular setup that we're getting data at each scanning point. This region, as you can see here, in the middle is where we expect to see most of the fatigue damage when this sample is subject to fatigue loading. There are multiple ways to define the features. Okay, and for example, here you can index each data scanning data point, a scanning point here. Then you can define your S and R, where S is the sample points features representation, while R is the reference point feature, which you acquired from a point which is away from the region of interest. So you can try to remove the baseline information using the normalization or the what we actually use as a reference data point here. For the time domain features you have for MBN, well, let me take a step back about NDE data processing. Depends on the methods you are using. There are different ways of acquiring the data, and You can either acquire that in the time domain, the signal will be a function of time, or you can acquire that in the transform domain. For example, you can have the Fourier domain data acquisition. Yesterday, we talked about an example when we do the microwave imaging, and if you use a VNA, and you can get a frequency domain data acquisition directly by VNA, frequency sweeping. Of course, you can get the data acquisition in other domains. Depends on your sensing methods. The data processing NDE. If you look at the method you're using, I would say there's no much difference when we talk about generalized data processing techniques. If you take let's say, introduction to signal processing course, not necessary for just NDE application, you'll see a lot of techniques can be used here in this course. But the thing that is important that you should know is the signal processing itself does not make much sense unless you understand the physics of getting the signals. Let me say this again. So signal processing itself, you can have any techniques that you learn either in time domain, in frequency domain, okay? But itself does not make much sense until you, or unless you understand how you get those signals, or the physics of getting those signals, or the way you do the sensing or imaging. We can see this clearly from here, right? The way you process a time domain signal from NBN, you have to understand the physics of here and how you are getting those signals. Then you can find your features accordingly, right? So people were debating, and I'm sure people are still doing that, sometimes make mistakes of signal processing for NDE is you just treat all the data as a generalized signal, then you pass that to, for example, a black box type of model, for example, neural network, and hope that the neural network can help you to classify or predict. Sometimes it will work, but most of the time it will not work well. The reason is you don't really understand the physics very well. Just blindly hope that any model can help you to find some kind of nonlinear mapping or some kind of fitting to solve a problem. So that is not a very wise way of doing data processing for NDE. Well, for NBN, you know this is a micromagnetic measurement. And based on the signal you are getting, that you know in physics, the signal in the time domain will be distorted because of the microstructure changes in the material. And there are work out there trying to understand how the signal distortion or the way the signals are distorted related to specific physical property or the change of the physical properties there in the material. And although we did not present any results on the modeling here, there are work about a few decades ago starting understanding the ambient physics using models or physical models. Okay, that's very critical. And I highly suggest you follow the same philosophy when you do your own data processing for any NDE methods. Well, let's come back to this particular signal we're getting for this particular application, that you can model the ambient profile signal using a mixture of two Gaussian distribution approach. The reason is you'll see that the signal here, the yellow signal, is being distorted due to the microstructure changes. And it is also similar to a Gaussian distribution with a distorted dropping edge here. So you can use a combination of two Gaussian in the time domain and try to capture the feature in the signal. By analyzing the differences of those two Gaussian distributions used to reproduce the yellow signal, right? So this is a signal decomposition here. Then the difference between those two Gaussian signals, for example, in the peak, we call this ambient signal peak differences, or the widths here, we call the full width at half maximum. We can use that to correlate that with the physical properties. For example, the ambient signal peak represents the movement of reverse domain walls from the pinning effect of dislocations, grain boundaries, and/or inclusions. And the width of the signal here in the time domain denotes the distribution of domain wall pinning strength of phase boundaries. Those are the knowledge you will get by understanding the physics of NDE method. Well, there are also, the difference, as you can see here, besides the peak. So the difference highlighted from the difference of those two Gaussian. You can also use that to correlate with the physical properties. More features can be extracted in the time domain signal. As I said, based on understanding the physics of it. Well, we perform simple Fourier transform. Then look at the signal in the frequency domain. You can get the maximum frequency spectrum amplitude. Well, you have that happen at, you have had the maximum frequency component from the signal due to the periodic excitation. You can also have, you can also have the frequency for maximum spectrum amplitude happen at this peak here, and energy is always a good way to look at the signals in both time domain and frequency domain. Here we just choose the ambient energy in the frequency domain, and we know that it related to grain boundary misorientation angle that influences the arrangement of magnetic domain along the boundary. Okay, so after we extract those features, we work on certain samples on, they are subject to different loading cycles. Well, we don't know, or we didn't know at the time, exactly the fatigue life of each sample, but we know that it all starts from the Preston stage and is subject to loading, and we know the ground truths for some of them, and we also know some of them has failed prematurely before its design life. We'll make the NDE measurement, when most of the samples were not, failed at some midpoint of this fatigue cycling test, and we get the NDE data in the middle. So the setup of this experiment like this: you have a sample, you want to study the fatigue life of it, and you want to see if we can develop a NDE method to understand the fatigue stage, particularly here the early stage of fatigue before we reach any macro scale damage that you can visually see in most of them probably you can see from naked eyes, but some of them you cannot. But it can be picked up by any sense, method sensitive to the surface breaking defect in the metal, for example, eddy current or ultrasound. But before it reached to the onset of a macro scale damage, you are using NDE to interrogate the material, the sample, and get information. Actually, this is a big project that Michigan State is part of it. There are other university teams that are working on different methods for the same set of samples. So those samples has to start from pristine, fatigue, then for some cycles, ship it to different research teams. So MSU responsible to getting the micromagnet measurement and nonlinear eddy current measurement. There's other groups in the United States. They're taking other measurement, for example, ultrasonics, optical, and so on. Then we do analysis for each individual method and see which one will give you the most sensitive measurement that you can tell the fatigue life of each of this material. Well, if we label the signals by knowing that okay, this is what fatigue life it is, and we can also define the categories of fatigue to low, mid, high fatigue, and of course a failure stage is a crack stage. You can also define a fatigue life as we introduced last time in our introduction class. This is a percentage from 0 to 100%. Right, so we plot the scatter plot based on the limiting information we had at the time. So you can see this is a plot of one feature, the full width half magnitude versus the fatigue life, where we color coded them based on the information where it was. And you can see there's a change of color. Some of them change from mid fatigue to low fatigue, some of them change high fatigue to mid fatigue, and so on. The reason is there are different time points that we use ND method to measure or try to assess the fatigue life. And at data point number one, time point number one, we apply different ND methods. We get assessment. Then we let the sample to subject to the fatigue testing again. Then some are going to fail, some are still going to not fail. So we stop. And based on those fatigue cycles, we calculate fatigue life again. And we realize, okay, some of them we thought they were mid fatigue at mid fatigue life, but it turns out there's a long way before it can actually fatigue to failure. So we'll change that to a low category and so on. So you can see this is actually mimicking what we're seeing in the actual measurement setting, that when you are looking at the actual systems, there's no way that using just a single time point measurement, you can know exactly what's going on for an entire history. Here, the entire history of fatigue life. A simple analogy that I want to bring this to my students is it's just like you open a book. Okay, you open the book. You don't know how many pages this book gonna be, and you open book till page. You see something at page 100, and it is very difficult to tell you, okay, how fast you reach to this page 100, how fast you read it, and also you don't really know how many remaining pages for this book unless you finish this book till the end. So this is actually a challenging problem, but if you read this book and try to sample at some discrete point, so you look at time point number one, you reach 100 page 100, then you keep reading, or you have some idea of how you're going to read. Then after some time, you reach page 200. Then you have more information, how you reach from 100 to 200. Then the way you interrogate will give you some information about this book. So this is not a perfect analogy, but this is analogy tells you the philosophy of doing the experiment here. And for NDE methods, I think this is also a good example for you to sample at different time when you try to assess the condition or the status of a system at different or discrete data points. Okay, so with that, let's move on. Before we present the data, let's introduce the series of the second NDE method we use here for this early stage fatigue study. This is the nonlinear eddy current problem. All the previous discussion, I believe, we talk about eddy current measurement, and everything, I believe, at this point so far are linear, which means that you have some excitation, then the response you should expect a linear response. In other words, if you increase the excitation, amplitude by a factor of 2, then you should expect the output signal also increase by the amplitude also increased by a factor of 2. That's the property of a linear system. But for nonlinear eddy current, you don't have that linear property anymore. By walking in a nonlinear region, when you try to subject the material in the strong magnetic field, so the material will be magnetized to a nonlinear region, so you won't have that linear relationship between your input and output for the eddy current measurement. So the nonlinear eddy current has been successfully applied to evaluate the case-hardening profile problem that we showed you before, right? So now we try to adopt this to this early stage fatigue study. So this is a example of showing you the input-output relationship, or the linear eddy current and nonlinear eddy current. And I believe there's actually a typo here by my student. For the second figure, the legend, the blue should be the output, and the red should be the input. Right. So so the green and the blue are the output signal, while the red is the excitation, and the NLE response signals contain harmonic components. If you perform the Fourier transform of those signals, you'll see harmonic peaks in the frequency domain that correlate with the microstructural properties of the material. So this is the setup for the nonlinear eddy current experiment. You have the signal generator, power amplify that. The key thing here to have the nonlinear eddy current excited is you're going to have a strong field. So you can do that by introducing the high magnetic permeability material in your magnetic circuits there. So you can saturate or make the material close to the saturation region to generate nonlinear behavior in your output signals. So one way that you can get here the fatigue sensitive information is to use differential probe. Well, in eddy current, linear eddy current, you also have differential measurement. We also just published a paper recently, and there will be another paper coming out that we demonstrate the differential patch antenna or patch sensor at the microwave frequency. So the idea of differential measurement is, different methods are going to have different way of defining how you do that differentially. But the basic principle is you are doing some kind of subtraction in your data acquisition. So instead of actually doing that in the post-processing of the signal, but at the sensing stage, you are doing some subtraction there. It's either subtraction from the signal from the same location, you have the differential configuration of a sensor there. For example, you can have for eddy current, you can have two coils very close to each other. So you can do a differentiation there at one location, or here you can have a reference point far away from your measurement location. So you can have a differential operator apply by when you're getting those two signals measured at two different locations. The assumption here is at the reference point that you won't have those fatigue information, but the underlying baseline information going to be the same, right? So that's assumption you have to make before you do this differential measurement. Okay, and now you're going to collect it at the same location, and also we chose the same reference probe position for NBN and NLE, so we try to minimize the uncertainties when we consider using different NDE methods for the same set of samples. Okay, so features for the NLE that you are mainly interested in the nonlinearity, and the nonlinearity will be well represented when you looking at the harmonics in the frequency domain. So you look at the frequency, you have the first harmonic, which is determined by the excitation frequency, and because of nonlinearity, you'll see the high order harmonics. And I think nonlinearity properties of nonlinear NDE methods is something that is still not very well understood. And if you look at nonlinear ultrasonics, right, that's also something that will give you very interesting results when you if you understand what you're doing in exciting your nonlinearity in your measurement there. So I believe that this is something that will have richer information embedded in acquired NDE signals. Some observation here before we move to data processing. We realize that all the harmonic peaks show higher amplitudes and variation comparing to even harmonics, and this gives us some prior knowledge when we actually process the data, and this can give us some idea what features we're look into. This is the same. This is a correlation study. We want to correlate with the fatigue life with the NDE data. As I just said, we're just like probe a sample at different time points, and we want to correlate the fatigue life of that sample, or here this particular stainless material, to our NDE data. And the data here, I mean the feature or features of the data, right? And there are different NDE methods being done here. I just presented two. As I just mentioned, there are more NDE measurement being done using different methods. And if we can gauge the fatigue life using NDE measurements, this will have very significant impacts when we try to understand the materials and the materials change over life of service when it's subject to fatigue loadings. So we adopted time domain and frequency domain approaches after we do the data processing in both domains. We can also do principal component analysis. We can do neural network. Here, because of randomness nature of the signals, we adopted probabilistic neural network. And there are some preliminary results on data fusion and uncertainty quantification. And I believe this work is done in 2020. There's already some papers published from our groups, from our group, and from other groups working on this project, and you can actually find that from Google Scholar. We adopt the same answer quantification analysis approach. This is a very simple way of doing it by looking at a standard deviation of a subset of measurement each time. Then you can calculate that statistically to get the standard answer quantification uncertainties from the measurement there. So show you some results that we try to understand the time domain features versus fatigue, frequency domain features versus fatigue from different methods. So here this shows you the features we had in both time and frequency domain. I believe some of them on the bottom are frequency. So the title here is a little bit off. Let me see. Yeah, though some bottom of them are not just time domain. So it's time domain and the frequency domain features. And we see that you'll see some trends here. If you look at the scatter plot, it's difficult, but if you look at the mean, you'll see the monotonical relationship between the features and the sample category. Well, sample category here is a simple categorical classification of the fatigue life. Well, ideally, it would be nice to have a real number there from 0 to 1 showing you the fatigue life. But it's quite costly to do that if you want to get a lot of data points along your fatigue testing, right? So we just using those category to label them into low, mid, high, and failure or cracked here. And you can see some of features are sensitive to that. You can have the peak changes, FWHM changes versus fatigue life, which give you some hope that you can actually quantify the fatigue by using those measurements. Well, you can also look at the statistical distribution of those features. And this is another way, I'm sorry, this is just play automatically. This is another way of looking at the data. And instead of just looking at the mean, you can also look at the variance of it. And you can see there's some trend there with the mean and also the variation of it. So you can see, for example, for the peaks, the low fatigue has large variations. And for FWHM, the low fatigue also have large variations of the measurement there. And also there's a slight, decrease in the mean value of each of them. Okay, so this is some interesting results we got to understand this challenging fatigue life assessment problem. Well, for NLE, when we look at this in frequency domain harmonic peaks, there's no monotonical relationship being observed, right, at the time, right? So, which means that either we will understand the physics better by improving the signal we're getting from NLE, or we have to switch to a different NDE method to do it. Well, for the data analysis, we can also look at that, try to classify or group or cluster those data and try to correlate that with the fatigue life. One well-known method is called PCA. The fundamental of PCA, I'm sure probably most of you know what PCA is, principal component analysis. The concept of PCA is, here we have, for example, a number of features for a number of samples, right? So you have those in the feature space for different feature vectors. Well, we don't know what features will be the most significant one. to explain or try to understand the differences between each samples. One way of looking at it is using the variation, the variance, the variability among those measured data. So PCA is actually a mathematical tool that you can decompose those data into different orientations, different axes, which are orthogonal to each other, and you sort or rank them in a way that the first axis or first orientation give you the largest variance in the data set. Then you have a second one, the third one. So that's a simple explanation of PCA. So why PCA? Well, PCA is a way to do data dimensionality reduction. So when you talk about PCA, some people just use PCA to do the data dimensionality reduction because, as I just explained, you are trying to find the orientation or some axis or orthogonal axis that you can use that to decompose the data and its information to get the largest, the second largest, the third largest variations in the data. So you can only pay attention to those significant directions or features. Here, the features is different from the physical features we extracted. So you'll see those feature space after doing the PCA, but you lost the physical meaning. So this is one disadvantage of PCA, that after you doing the PCA, you lost the physical meaning when you look at the principal component number 1, principal component number 2, and so on. Okay, so what we did for this particular problem is we extract the principal components. We found that the extracted principal components for the first couple of directions that we can use that to explain 98% of the variations in the data. Or in the PCA, you know that you say, okay, this contains 98% of the information in the data. But the information here is just explained using what I just said, the variance of the data. And we use different features combination to perform the PCA. Okay, so for example, case number 1 for NBN, you can have all the time domain features and energy in frequency. Or in case number 2, you can have all features possible. So you have a different feature matrix as the input to the PCA. Then you can get the PCA, the principal components. Then you use those principal components as your new feature and try to differentiate or classify the data. For NLE, there's different way of choosing your feature, matrix before passing into the PCA. So we just try a different one. So there can be more cases of pre-processing data before you use a PCA. So from the PCA analysis, then you can see I can choose the principal component 1, 2, 3, and see if they are sensitive to the fatigue life changes. And here we try to find the relationship between the principal component versus the sample category or the fatigue life here. And you can see we have a steeper relationship of PC versus fatigue life, right? Although we don't have too much understanding of the meaning of the principal component readings here, right? But this will help us to understand how we can differentiate or classify them into different fatigue categories. Well, this is a different way of looking at the principal components, right? So you can see the mean has a monotonic relationship, and also you see the variance as one statistics when you analyze the data. You can look at the principal component features, in the feature space. Again, those are the principal components features. Well, you can see that I try to group them or cluster them just using PCA data. Here, this is a two-dimensional plot, or you can treat this as three-dimensional plot. If you combine those two-dimensional plots at the same time, you can plot them in three-dimensional space. So you can look at those fatigue samples versus no fatigue ones. Well, they have a very good separation here. Well, for fatigue at different stage, this is still mixed somewhere. It's difficult unless you group some of them, from mid to low or mid to high, right? So this is the PCA results from the limited 30 samples we had. Well, the PCA is now working perfectly, right? And so let's see if we can use neural network, and here the probabilistic neural network, to do a better job. Well, as I mentioned at the very beginning, I'm not a person who would suggest to do neural network from the very beginning unless you understand the physics well. Well, I don't expect that a neural network can solve all the problems just mimic the human brain, right? Because that is a very simplified model, and if you start from no pre-assumptions, then your data will not be very structured and well understood. So very highly likely it becomes a blind data coming in. You can have some hard to interpret results coming out. Well, the advantage of probabilistic neural network is you can work with smaller data sets, particularly when you have limited training data. In this case, that's true because we only have about 30 samples here. And you have the Gaussian function centered the associated feature vector in each class. So you can have some probabilistic nature in our neural network. The input is the features of NBN and NLE data. And as I said, you already select those features based on the understanding of your NDE methods. And your label, you want to, the neural network help you to achieve is to find the remaining life or remaining cycles to failure. So you label the data based on the information you have, and you want to achieve a multi-class classification through neural network. Right. So you can have more details from the fine prints here. If you want to try similar problem using problem neural network, so I would suggest you consider this method when you have limited data set, and you can have fairly good understanding of what you are passing into the neural network. One concept that we introduced here is you can use the classification index, which is a softmax function to obtain the optimal vector, and use this to give you the classification confidence that you can understand your classification better. This is another way of looking at the uncertainties in your data classification. So you can have a different confidence level when you classify them into different categories here. So the basic idea here is to use a negative log likelihood function. So you can use that to describe the classification results with some confidence level. And this is correlated to the loss they're dealing with, for those neural network classification. So one example here just shows you that when you have input, vector, you pass this to PNN, then you're going to have the classification of your results into different category with different confidence level using this classification index. And from this particular result, you'll say, okay, I will classify this into a low fatigue because I'm getting the highest confidence from this softmax output function. So so the results for these, the data set we had, we have in this case 26 samples. We exclude the cracked samples because that will be the outliers for our test. Then we randomly select 23 samples for training and 3 samples for test. And you should randomly select those samples and do this at multiple iterations. This is similar to what we are doing for bootstrapping. Okay, due to limited number of samples, that it doesn't make any sense to just train with a smaller number of training data set and test with an even smaller number of data set. So you can use this random selection strategy and do multiple iterations or trials. So you can have the accuracy as the average of the calculated accuracies from all those trials or iterations, and you just select those with a threshold to calculate the final accuracy. If the accuracy is greater than the threshold percentage, then you calculate the classification index for each correctly classified samples, then do an average of that to get a final CI. Different ways of defining PNA inputs, similar to what you do, what you did for PCA. You can also define your PNA inputs from different methods. Again, you need to have your prior knowledge or expert knowledge when you select those inputs. Okay, it will not work. You just blindly throw everything into a neural network. Although a lot of applications we see people are doing that, right? But try to avoid doing it. So this shows you some of the results we had by using different combinations of inputs, features for the inputs. Then you can have the output and tells you the performance of those classification, right? Here we get the initial results at, I believe at the time we get about 75% accuracy, for the classification of them into different fatigue levels. The data fusion, this is an ongoing effort. We haven't published these results yet. This just tells you that we can do fusion in the feature space here. Hopefully we can improve the performance of the classification and also try to quantify that performance using an uncertain quantification metric. A simple way of doing it is using a weighted average, right? We've seen weighted average approach in our prognosis. So actually, you've seen different ways of doing that. And remember in our prognosis study for, let me see what study that was. That was the composite of, the fatigue failure in composites subject to external loadings, and using different ND methods to do it. We try the weighted average of the data. We also have the joint likelihood approach. At the time, we definitely see the joint likelihood to give you a better performance than weighted average, because you don't have much information how you're going to choose the weights. Right here, we see that we can use a weighted average, but we have to select the weights carefully. You don't want to evenly distribute the weights for each features, right? So you can have the weights to be assigned, as we have different cases here, like the weights we call accuracy weight, or we can have the accuracy with CI confidence index weights, right? So you can have different strategy to fuse those data together, then rerun this data classification, right? And then compare the results with original single sensor classification results. So we definitely see that the fusion help us improve the accuracy here, and particularly when you have the weights by considering the CI into it, then you can have a higher CI and also have a higher PNN accuracy after we do the data fusion. This is some preliminary results, and this can be further improved. We believe by understanding how we'll select the features and how we can better weigh them into our machine learning model. And I think I can skip this. This is just some takeaway from this particular study. But as a course here, I think what we should get from this lecture is how we can apply feature selection, feature extraction on the ND data when we have a better understanding of the physics of the ND measurement. Then we can use different ways of data processing, particularly for the classification problem. You can also use that for prediction problem, as you see in previous lectures. So the choice of ND methods is important, and you should have good understanding which method to choose. The feature selection and extraction is important, and you have to rely on the physics of the chosen ND method. Then the classification, or in general, the processing of those data into, for example, dimensionality reduction approach, neural network, or in general machine learning approach, that you have to understand what you've done in the previous two steps. And this is, a method that I want to convey if you want to extend this to a more generalized approach that you can do or get from these lectures. So some future work. We are continuing to do machine learning assist data processing and multimodal data fusion beyond EM measurements, how we can combine that with optical, with ultrasonic, and so on. And we are always doing global understanding quantification and reduction. And hopefully one of my PhD students going to graduate in 2023, and her thesis is focusing on the understanding of a global understanding quantification for a generalized ND methods. And a holistic physics-informed AI, I believe that is definitely important. I always emphasize understanding physics before we're doing any AI work. Okay, so with that, I'm gonna stop for the first module of my class. Perfect. I am 2 minutes before my intended lecture time. So with that, I'm gonna take a 2-minute break and answer any questions before I actually go to I'll call more like a lab session or some case study that I did not have time to go over yesterday on structuralized sensing technique. Okay, so let me take a short break. So if there are any questions, we can have a discussion in class.
Let me check the chat. If there's any, I don't see any chat. So any questions from the audience?
So let me share my screen again.
Yeah.
Okay, I realize there are more online participants this time, which is good. Um, Let me share the other. Okay, let's wait for 1 more minute and let me share my
No
screen.
issues. You can take your time. No issues. You can take your time.
Yeah, I'm just setting up my slides here. So,
Okay.
okay, I believe you guys can see my slides now.
Yeah, we can see it now.
Okay, very good. So this is more like a lab session, and I just want to go over as many examples I can at this GAN course. Um, the purpose of doing this is not just for education. I think, well, that's the main purpose of doing education, so we can have a better exchange of knowledge through this GAN course. Another thing is I want to expose the students to the recent advances in NDE, particular for some emerging applications out there. So this problem is, I think I mentioned this a couple of times, and this is um, you know, to me, I think a very critical problems we're facing when we're talking about energy transportation, energy independence, and so on, where we focusing on the um, energy pipelines. Okay, so pipelines has been there for decades, right? The oldest pipeline you see, uh, there's actually going to be thousands of years, right? You see that in those ancient um, civilizations that people use uh, you use clay, use ceramic, use stones to make pipelines, right? But now, for transporting the energy, here the energy particularly, I mean the like the oil, crude oil, natural gas. Um, those are the pipelines we're focusing here, right? Of course, there are other pipelines out there for them, for the water pipes, sewer pipes, and so on. Um, and recent years, when we are talking about decarbonization, reduce the greenhouse gas, and so on, people are looking at more cleaner energy globally. Then there are active research here at Michigan State with federal agencies in the U.S. Um, and there are a lot of ongoing projects, not only U.S. but also in Europe, in Asia, is if we can use clean energy, for example, hydrogen, right? So how we can transport hydrogen safely. There's a very hot research topic, and how we can utilize hydrogen in our daily life. So all the research here have implication of achieve that goal. Although we are only focusing on the small sub problems here, but this has a very big picture when we're looking at this energy transportation problem out there. So with that, hopefully I give you better motivation than what I'm going to show you from this picture, because this picture is a limited scope that we try to look at the plastic pipes and the damage to plastic pipes, um, and how we can understand the degradation and failing mechanisms for plastic pipes, and using new sensing technologies to not only detect but also to categorize them and lead this into the answers that I just posed, with different challenges identified. Well, for plastic pipes, it has been out there also for many years, and for the distribution pipelines. Now, in the United States, I believe that same thing in India, that more and more distribution pipes now are being installed or repaired or replaced using plastic pipes. Um, Before that, you'll see a lot of metal pipes, out there, but they are now more and more replaced with plastics. Um, and the understanding of those complex network and with new plastic materials, how that gonna work over many years, um, that's very important. Okay. So with this, we define the concept of unpickable pipeline networks. I mentioned this briefly before. Um, and the pipeline, as you can see from the bottom, the middle one, it has a lot of challenges if we try to inspect that using conventional tool. First of all, the diameter is very small. So the PIG, or the pipe inspection gauge we talk about for large diameter pipes, will not work well. It will not fit. The second is the geometry, or the complexity of those small diameter pipe networks are very high. Then you can have a lot of 90 degrees band, vertical, sections, and the change of diameter, and so on. So it's quite difficult to maneuver any inspection tool inside those pipes. The third is we want to have a high resolution NDE tool, or here the inline inspection tool, that we can get information we want to evaluate the integrity of the pipe. So this shows a roadmap how we reach this point in 2022 for this particular technology by combining the sensing technology. Here is a structured light sensors. We first got this idea materialized into a funded proposal in 2016. We got a sponsor from FEMSA, U.S. Department of Transportation, and then we work with industry, the industry consortium, OTD, and we integrate the sensor later on a robotic platform, which is a smart snake type of robot. Then recently we expand that into a AI-enabled shared control robot by working with computer science groups, right? So this is where we are, so we can achieve a comprehensive inspection solution for polymetric distribution pipes, and which are intrinsically unpickable. So this is the project teams and objectives we had about 2 years ago after a few successful projects, as I just pointed out. So NDL LMSU, we are responsible for design and develop a structured light sensor, which will move inside the pipe. So we call this endoscopic sensor. It's high resolution and sensitive to different type of defects. Will give you surface features in a featureless, or most of the time featureless, plastic pipe. We call this featureless because the surface of a plastic pipe is very smooth. So it's very difficult for you to actually do a data reconstruction while knowing the correspondence issue, that you know where your sensor is when you are taking the data. We also want to have an automated scanning process, including the auto calibration of a sensing system. We just submitted a paper, I believe, last week. So we can have auto calibration capability. We also want to have the um, data registration capability there. When we have the sensor vibration, we have a sensor system slippage issue, and so on, how we can better register and process the data from an NDE perspective. There are two other teams who work together. One is the Smart Microsystem Laboratory at Michigan State, where they are experts in developing flexible robotic platforms. So they're responsible for the navigation and mapping of a robot when we do the data collection. And this is a trend. You've seen this in NDE3 robotic platforms to give you high quality NDE measurement. And we'll see that more in tomorrow's lecture. So I will spend 2 hours talking about the new paradigm when we talk about the NDE 4.0, particularly the new technology we've seen out there. For example, Internet of Things, communications, um, on the scope of Internet of Things and robots, how we can get smart NDE systems. So that's the lecture for tomorrow. Don't miss that. Then we also work with human-centered robotic laboratory at CSM, Colorado School of Mines. Now this group has moved to University of Massachusetts at Amherst, where they implement a shared control method based on reinforcement learning to allow the user to control the robot more easily and safely. So I just going to go over some of the tasks here. The results here are 1 year old, right? So I do not present the latest results, but I'll be very happy to talk to you and direct you to the latest reports in public by DOT based on our work. But I think this will be a very good discussion and case study that show you each components of a more holistic solution for robotic plus AI and the solution. Some of the work here is not done by my students, so but I will just give you an overview of that. Right. So the first task is the miniaturization upgrade of a robotic platform. You'll see more examples tomorrow. For this particular application, you'll see we need to achieve the robotic miniaturization that we can work for the small diameter of distribution pipes. The diameter for that is ranging from anything between as large as 8 inches and as small as less than 1 inch pipe. Well, 1 inch is 2.54 centimeter, right? So if you convert that into metrics, this is about 2 centimeter diameter pipe to about 20 centimeter diameter pipe. Right. So you need to have a robot about that size and can maneuver in a complex pipeline environment. You want to achieve blind spot free sensor scanning, accommodation for practical field operation as well. So I just want to show you some results of the robotic design. This is the initial design in CAD. We start with a large diameter design work in the 6-inch pipe. Then we reduce the diameter of this robot. And everything's been 3D printed. So all those components is not going to go through a complex manufacturing or conventional manufacturing process that you can easily design and make your robot by 3D printing. Okay, and this robot can be compressed, can retract with this multi-link design. So think about this more like a snake, but it's a multi-link snake. So the diameter, if you compress it, it can be smaller than when you retract due to the spring there. You can have this to work in a large diameter pipe as well. There are some design, I will not go into the details, but just shows you how we do this, starting from computer-aided design environment. So everything will be designed there. You can start from the joint design, wheel design, and so on. Everything will be understood at this stage. And recently, we are adopting a virtual environment simulation that you can have robots simulated and operating in that environment and integrate some basic sensors there. But the new sensor technologies cannot be adopted in that environment yet. So this shows you the finalized CAD design where you can see the robot that can fit inside a 4-inch diameter, inner diameter pipe. The sensor is not being shown here, and in this project, we will mount a structuralized sensor at one end. When it's moving, then you'll have the sensor collect the data. Well, as you can see, it's very difficult to make the sensor always on axis or at the center axis of the pipe, right? That's almost impossible by considering the compression retraction of those robot and also vibration when you're dealing with the data collection process. So this brings challenges, data processing in sensing. So we're going to talk about it very soon. So some actual pictures about the assembly, which are all 3D printing materials. They can be easily assembled and disassembled and replaced for maintenance and change of design. This is the Omni wheels. Then we can have different set of wheels, and for different diameter, you're going to have different design. This is assembly without wiring. You can see the test pipe in the lab behind it. So this robot can fit into this pipe, move there. We use a Raspberry Pi as an embedded system solution to control the robot. The robot is designed to be either tethered, untethered, or wired or wirelessly. You're going to see a demonstration of wireless in a video very soon, that we can deal with the data collection on board with some onboard computing or edge computing capability. The data will be stored or it can be wirelessly transmitted to the above ground location. And you can do data reconstruction there. There will be 5 individual motors, a motor that can maneuver the robot at different speed, different rotation, and so on, and different direction. Then you assemble this, you add the wires, you add the batteries, you add the Raspberry Pi there, so you can have this under control. Then you have this robot also integrate with the sensor. So you can see this is the picture showing the robot integrate with the sensor moving inside the pipe. This is just a picture, and we use a clear pipe to show you when this is moving inside the pipe. This is 6-inch pipe when this is moving. I believe this is a video. Yes, this is a video. We don't have really need to have the music there. Just pretend you have some cool music in the background. But anyway, so this is the first demonstration of this robot in the pipe. And you can see this. This testing is actually done in one of our students' apartment because of the pandemic lockdown. So the lab cannot be accessed. So some of the development actually is done in the apartment building. Okay, so I think I can skip some of the details here. Then this also show you. I don't think you can hear the sound here. So this is how you can remove the wheels in the end. Then the redesign and modification of the initial rover platform, as I said, we already have several projects before that. So we redesigned it, then integrate the sensor of the structured light sensor here. There's been paper published on this endoscopic sensor on IEEE sensors journal, so you can read it if you want to know more about this sensing technology. You can search the name of electronically stabilized sensor or structuralized sensor and search my name. Then you can find that paper from IEEE sensors. Okay, the second task developed with NDAL is we redesign and optimize the structuralized sensor so we can reduce motion effect for 3D reconstruction and also achieve the 360-degree reconstruction. The calibration has been completed. As I said, this is 1-year-old results. We just submitted the paper last week for the auto calibration. So everything's gonna be automatically done, so we don't have to do manual calibration when we assemble a sensor in the system. And for the point cloud registration, we demonstrate that using the auxiliary or additional you know, IMU unit, initial measurement unit on board, that we can improve the registration capability with additional measurement data. Right. So this is an ongoing effort. I expect to submit that work to NDT and E International or IEEE Transactional Industrial Electronics very soon, maybe in the next couple of weeks. So this shows you the picture of the structuralized sensor. It's an endoscope sensor. The idea how it works is you have a structuralized source or projector at the middle part of the sensor. It will project through a oblique angle, and the light will pass through this transparent glass tube to the in the wall of the pipe, get reflected, distorted by damages if there's any, and captured by a wide angle camera at the tip. Right. So this is a design which we can miniaturize the diameter of the sensor. It can fit to a pipe as smaller as 1-inch diameter. We also synchronize the data acquisition. The new design have a additional LED sensor at the LED light at the tip of the sensor, so we can synchronize the data acquisition to get both structural light information as well as visual camera-based information. And by combining both, we can make this into a RGBD sensor, which you have 2D information and 3D information. Well, the 3D information need to be obtained through 3D reconstruction of the structural light measurement. So this shows you simultaneous LED white light and structural light acquisition from this sensor. You can see from the left is the structural light measurement. This sensor prototypes still has not the 360-degree capability, so you'll see some loss of data due to the wire there in the sensor blocking the light when we are projecting that to the surface of the pipe. But the right is the synchronized data acquisition using the camera illuminated by the LED white light. Okay, so you can see this is data collected with a single sensor, so you'll get this at the same time. So the structure light will give you a 3D reconstructed surface, while the right one will give you the 2D information coming from it. One improvement that we actually built and tested is to use a more like a stereo type of sensor. So you have a light source P, and you can have two cameras configured orthogonal to each other. In that case, you'll have the entire 360 degrees of a pipe reconstructed. So the math behind that, you can find that in our publications, and how we can actually reconstruct the entire surface of the pipe. This is the idea. You can show this from the real camera data from camera 1 and camera 2. You can see loss of data for one of them, while the loss of data from another one is actually off by the angle of 90 degrees. And by merge those two together, you can have a reconstruction of the entire pipe. But you have to deal with the offset of those two cameras in space, then doing that through data processing, right? So you can see, for different camera data, it appears differently, but through data processing and reconstruction, you can merge them. And even with noisy measurement, you can have a very good data reconstruction on a single ring demonstration here. This is auto calibration approach, and the idea here is you can use the cylindrical geometry and help you to calibrate the sensing system without manual intervention. Okay, so the solution is impose geometric constraint from the cylindrical geometry, as I mentioned, and you calibrate the sensor automatically. So you can have some initial estimate by minimizing the difference between the calibration pipe radius and the estimate radius from the reconstruct points. So you have some, estimation done. Then you can use that information and to perform the final calibration by the concept of ray cone intersection and ray cinder intersection. Quite complex math behind that. It's an optimization problem, so we can use that to achieve the calibration of the system automatically without human intervention. So there's multiple artifacts needs to be addressed in this auto calibration. So further data processing for artifacts reduction there, and we can remove these artifacts. You can see the reconstruct data from this point cloud representation is can have less noise before and after the fine tuning of this correction of artifacts approach. For the point cloud registration, there's some work to be published. Also, there's some ongoing work that we can work with industry partner. The first is local positioning. We want to know exact location of the pipe. Use features we're getting from the data, and also from the gyroscope or accelerometer data. For the past year, we implemented using IMU, so we can get a gyroscope information, data information, also the accelerometer information to help you to solve the rotation and slippage issue, respectively. So from gyroscope, you have the information for rotation angles, theta, and for accelerometer, you have the slippage information when this pipe is moving inside the pipe, with sometimes with a smooth surface, so you might have a slippage issue there. For global positioning, there are multiple solutions out there. One is using the fiber optic to get the 3D positioning information, right? So this is some work we haven't done yet. So we mark that as a red box here. This shows you how we can get the information to help us to register different different information from different measurement tool together, right? So this is proprietary information yet, so we haven't published it. Okay, so this shows you the integration of a sensor and IMU unit. This is our first prototype demonstrated not on a robot. This is just on a 2D gantry, and this is actually a low-cost gantry with a lot of vibration. So we can also have a vibration in our data acquisition where you have this low-cost gantry moving inside the pipe, right? Because we don't have a robot, we don't have an actual pipe. So so if you have a high end scanning tool it's very difficult to introduce a vibration, right? So so you can have vibration actually here in this low end gantry scanning tool. From this setup, you can get the information as mentioned for better data registration. Also, we have to solve the sensor stabilization issue, and a lot of things actually been done in the sensor robot integration. So you'll see this is just illustration from literature showing you a camera mounted with a fixed relative position to a user-defined robot frame, right? Here our robot is different, but the concept behind that is quite similar. So you can use this idea and help you to do the optimization of the sensor with a robotic solution. This shows you the graphical representation of calibration. This is being done on camera-based data in the lab. We have this calibration pattern. You can see from camera and from IMU, there's a mismatch there, because you may have those rotation or slippage issue. Let me play this again. But with IMU information, you can actually correct that, so everything will be correlated together with a minimal error being observed here. This just shows the performance of using IMU. Then you can reduce error and actually track the changes in all different directions of the pad measurement based on IMU. Okay. I think I can skip here. I can play the video. Let me play the video. Let me stop sharing and play the video here. Let me share my screen. Hold on. Share computer audio. Movie and TV. Can you see my screen?
Yeah, we can see your screen.
Okay, very good. Okay, I'm gonna play this video. I don't know if the sound gonna be there, but anyway, I don't think that matters. So this is the
There's no sound right now, but I think
yeah, I don't think that we need sound. I can do the annotation. So this is a tethered snake robot moving the pipe, the first version, so we can have the tethered for the power and also for the data collection, data communication there. This is untethered wireless robot, and you can see there's a payload card there where we can have the hardware as well as a battery there moving inside the pipe. So this is how the untethered snake robot work in the pipe, moving forward and backward, also doing the rotation there. So you can collect the data in all angles. And this shows you one setup when we have a sensor at the front of the robot, then before moving into the pipe. You can see there are some low-cost solutions to cover the pipe to simulate that everything is on the ground, right? I think the students are kind of, creative. Instead of bury this pipe in the soil on the ground, that they cover that, use aluminum foils and cardboards. The reason for that because this polyethylene pipe is not completely opaque when you put this in the natural light in lab, right? So it will affect the, it will not appear completely dark. So you have to move the sensor, by in the pipe by covering the pipe, while we still can keep the light on in the lab. Yeah, so this is how it is moving. So I'll stop here. So when you're moving, this is our 2019 version, and you can collect the data, and you can do the classification of damage real time. So you'll see each frame is actually being processed in real time, and you will have some detection results or classification results in real time there. And the algorithm here is quite simple at the time. That we just using this structured light, get 3D surface, and then calculate the vector field where we see those differences in the 3D structure surface, then try to to classify them into cracks or material loss and so on. Okay, and you can also get the magnitude of the vector, so it can tells you the size of the defect there. Then, yeah, let me play that last part a little bit more. Okay. I believe I have other videos. Let me see. But let's go back to my slides again. Hold on. No, this is not one. Let me open the A4. Okay, very good. Let me open here. Hold on. Okay, I think we're back to the lectures. Hope you can see the share screen. Okay,
It's visible.
it's back. Okay. Okay, so the last task before we actually do the integration demo on the actual field condition, the last task is actually led by the human-centered robotic lab. Now at UMass is this AI capability. So this just give you the background of reinforcement learning. So the RL agent is able to perceive its environment. So it will take actions and learns through the trial and error. So we want to get at RL capability in our robotic control, and we call this shared control. So the shared control, the concept, instead of just have the human operator to control a robot, now you have another layer of um, AI using reinforcement learning that can help you to tell, okay, where to get the data, how to get the data better, and how to control the robot to a location that you want to get, a data, for example, you want to uh, consider environment conditions and take, for example, multiple rounds at the same location, and how you can optimize your sensing parameters and so on. So this is the reinforcement learning, and I think that group adopt the MDP, Markov decision process, for their reinforcement learning practice. Right? So I don't think this has any results to share, but I believe the publication will come up soon. If you're interested, I'm sure you'll see this maybe in the near future after today's lecture in this class. But just give you a basic idea. This is not done by my group, but I just want to show this is what's going on. And for robotic NDE, I personally believe this is a very promising area to look into. That you want to make your robot to learn by itself, right? And instead of having what we're doing here in NDE, we have the data, then we develop our learning model based on data we get. But integrated learning when we're collecting the data and have our data collection and the NDE process itself to be a learning process. I think that's something really going to be significant if successful. Okay, so this is just a quick demo, show you the Q-learning training. Well, this is not a pipe inspection application, but this is just something they show they can do this learning when this is more like a maze, home maze problem. All right, I think I will skip here. They have some video there. Um, I, I think this is from their group, but not for our pipe project. Okay, so this is some plan I just list for from our group. So this is a table we came out from NDEL. I deleted the commercial info plan for other components because I don't think it's appropriate to talk about this without their permission. But for my group, I'll be very happy to share. I think this is more suitable for a lab session discussion when we talk about the transfer of technology into the field, or how we can make our knowledge to be useful in practices. And when we talk about the concepts, the core ideas, the knowledge we learn from this course, right? This is a course that we more in a academic setting, right? But we will see a lot of those concepts can be materialized into an actual systems that will be useful into the industrial settings. Well, that's a goal for, I believe, for NDE people, right? For NDE people, we want to make sure that our applied research can be useful and have a short-term impacts to the fields that we're working on. So for sensing here, for this particular problem, I just want to point out a few things or a few directions that we think is important when we are developing our tools in the university lab. For example, for sensor optimization, that we definitely want to go to the industry-grade sensor fabrication by collaborating with industry, and we need to define the specifications when we want to work those, have those sensors work in a field condition, while we identify the answers to two questions here. And I suggest, as students, when you practice in this field, do the same thing. you first ask yourself what needs to be done, right? So this is I ask my group members to answer that what needs to be done. So this define our research and development tasks. Then why we want to do it. This give you an understanding of the benefits of it. Well, we have to be realistic about the benefits of a system we are doing, right? And then we have to decide, based on the specifications, all the interaction with industry will need to be defined into the first and the second questions answer, task and benefits. Then for the system optimization, for example, we want to have purpose-built electronics. This is beyond scope of NDE, but this is something that we should foster the collaboration between NDE people and a group of other engineers to do the optimization of the system. The graphic user interface optimization, this is more like a software development. A lot of human-centered research should be brought here. And we also have to consider a lot of things we usually consider in the industry engineering department, and how we can have a better interface and how we can have a better interaction of the operator and the technologies we are developing here. Accessories optimization, for example, I just mentioned the global localization problem, how we can get the actual information when we have the sensor or robot moving inside the on-ground pipeline networks. The last but not the least is the consideration for field demonstration evaluation before we actually move this forward into a commercialization plan or the commercialization product. So, for example, how to do a full sensor characterization in a field condition, right? So we need to do that before we move to the actual commercialization testing. So I think this is what I want to share with the students in this course is we are now at the end of this lecture. I hope to design this lecture in a way that we can not only learn the fundamentals in the sensing imaging, data reconstruction, well, under the inverse problem scope, but it's better to consider all those aspects that we're learning into a more practical problem solving setting. Well, the problem solving setting I mentioned here can be different things if you're working in different areas. But for NDE people, I think what we need to consider, right after the lab um, environment or the fundamental research, what we're doing here is going to do some form of field testing, increase the TRL number, technology readiness level number. Usually we're talking about 4 and 5 at the end of the lab environment development, and we want to move that to 6, 7. Then we can keep moving that into a higher number before we go to commercialization. All right. So for this course, we have one more lecture to go tomorrow. And in that lecture, we'll talk about industry and NDE, and we'll particularly talk about some fundamental research in the lab here at Michigan State. But I hope to have some time for open discussion tomorrow with the students about future directions and your interest after you taking this course. And tomorrow we have 2 hours in the morning, and I hope that we can have 1 hour and 30 minutes lecturing time, then have 30 minutes discussion. So this is like an assignment I gave you today, is to think about your own problem, your own interest, and we can have some discussion. So instead of me as a professor to teach all the time in this GAN course, I think I'd like to have maybe 30 minutes of discussion that we can have at the end of the lecture as a roundtable open forum that we can exchange ideas. I think this will be beneficial to everyone. It's beneficial to all the students and also beneficial to me as instructor. Okay, so that's a plan. I see there might be some questions um, for the chat. Let me see if I can answer that. Uh, Thank you, Jinxin Li, for your kind note. So your question is, what can be the flaws or constraints of such techniques in real-world scenarios and in ambient noise consideration? How to look at the impact of Earth's magnetic field effect on all this? Um, yeah, this is a great question, Jingchen. This is definitely something. I don't know about the first question. Is that related to the structure light, or this is related to the micromagnetic measurement or the early stage fatigue? Maybe you can type in that in the chat window while I try to answer your second question. The impact of the Earth's magnetic field effect. Well, uh, in this case for the ambient, I think the effect of magnetic field from the Earth, that's we had assumption there that we ignore it. This assumption that I believe it is valid for the ambient measurement for this particular case. But this is not true for a lot of other magnetic measurement case. And for this particular problem, let me tell you why it can be ignored. Because we have a AC excitation. We magnetize the ferromagnetic material there. There is a stainless steel. We can have different type of ferromagnetic materials there, and the field we are used to magnetize the material is much stronger than the Earth's magnetic field. Well, Earth's magnetic field is about 500 Gauss, if I remember that correctly. So also because this is a AC excitation, and we know the frequency we are looking for when we're looking at the response signals. And our filtering technique in our data processing is also designed and tailored for that particular frequencies. So we know what need to be filtered out, or we know the possible noise that are coming from. So even we have some interfering signals, data collection, that we should have a good way or good understanding of filter them out. Right. So this is answer to your first question. I hope that answer your question and that makes sense to you. The second, or your first question is what can be the flaws or constraints of such technology? I don't know if this ambient or structured light in real world scenarios, but this is indeed a great question for any NDE methods we're dealing with, or any NDE people that we're doing, and then we hope to have our technology develop in the research institution, in the research lab, and make that practical in the real world problem. Um, I don't know how to answer the flaws question, but I think I can talk about the constraints of techniques in the real world scenarios. For let's say we can start from the structure light, but for different NE techniques, I think the constraints are different. So for structure light, in real world scenarios, we have to deal with a lot of things, including different sources of uncertainties. And if you test a particular system in the real world, what you can have for the uncertainties coming from different aspects, from the sensor, from the robotic platforms, and also even from the learning model itself. From a sensor, you have to deal with, for example, different light conditions. We have some assumptions of the light conditions we are developing the sensor, but in the real world, that can change, right? And also a different condition of the pipe, different color of the pipe, and different geometry of the pipe. That will also affect our data. And this is true for a generalized ND practice, that when we have our technology, transfer that technology to the field, you'll see the constraints is many orders of magnitude higher than we're seeing in the field, in the lab environment. So I think this can be well studied for each individual technique. It's a technique dependent, problem dependent problem. So the last table here is one way of looking at the constraints in the real world scenarios and how we're going to solve that. So for the flaws for real world scenarios, then if I try to answer that based on my understanding. I didn't see a follow-up question from you, Jingchen, that uh, the flaws in the real world scenarios are also way more complex than what we're seeing in the lab. We can have real samples in the lab, but still that's not going to, produce the same complex scenarios in the real condition because, think about the concept I covered yesterday using Bayesian updating. When you have new data coming in, all your previous training, all your previous knowledge you have is based on what you already know, right? But in the real world scenario, there's a lot of uncertainties, unpredictable things happen that your data may have something you never know in your previous training, and that will cause problems. But hopefully, our work is trying to make sure that you don't have much unpredictable events, or your results will not be off too much based on well-developed or well-trained model before. So that's what I can share with you at this stage. Hopefully this makes sense. If you have more to discuss, you're very welcome to send me an email. Then we can discuss it offline, even after this GAN course. I think give lecturing at a GAN course like this, it's a privilege and also opportunity for people to get connected and also to share ideas, right? This is an idea of global, the G comes from, right? Globalization and the global interaction of researchers in the field. Okay, so this is what can I share with you. Thanks so much for the question, and I'll see if there are any questions. I think we still have 3 minutes before we continue our lecture tomorrow. Anything else that we can discuss? Don't remember we're gonna have an open discussion tomorrow, so get some question prepared, and I'll be very happy to hear if you can share your experience based on your experience of this GAN course, what you learned from this course, and hopefully I think I try to give you more motivation about learning the fundamentals and move this into a practical problem. Tomorrow we're gonna see more problems there in the real world problems, so we can have more discussion. Okay, yeah, sorry, Niraj, I interrupted you, so
No issues, no issues. I was just checking that whether are there any questions or not from the audience. So there's nothing in the chat window. You already addressed to the one.
Okay.
And any questions from your side about that assignment? So you can ask. Just there's some questions, yeah.
Okay. Okay, my microwave guy. Okay.
Yeah. Now this time my question is not related to microwave. Here about this assignment, lab assignment.
Okay.
Yeah, I need some hint to how to start these assignments. I have read that document, the assignment related document, but it is full of mathematics, and I required some initial start to write a code in MATLAB. So I have seen your site also related to this assignment. But I required some hint and initial start.
Okay. Okay, let me give you some initial hint. So you actually have you looked at the tutorials on that EDOS site? There's some tutorial there,
Yes.
and there are MATLAB codes there.
Yes.
Yes. Find a problem, a tutorial that help you to set up a similar problem. Their problem. There are also 2D, 3D problem that start with a 2D problem. This is a 2D setting. And
Yes.
you'll find some codes will be very similar to what we're doing in lab assignment. Find a similar problem there. Run that problem through. Don't forget about setting up your own MATLAB codes or write your own MATLAB codes for this problem, but understand their codes.
Yeah.
Then run the problem setting and reconstruction from there. And that's a hint I can give you.
Yeah.
Instead of looking at your own codes. But I believe probably you're in a stage of understand the problem now. So I suggest you run some codes there from their website, and
Okay.
and I think that will be helpful to you.
Okay. Okay. I will go through that programs and I will see.
I'd rather you spend some more time on reading that the website before you actually solve my problem, because the problem you're going to solve in this lab assignment compared to the example there is much simpler. So if you can understand the example there, I'll be very happy. Then you solve my problem.
Yes.
Okay.
I'm understanding this problem, but implementation in MATLAB is a little bit difficult for me.
Okay.
But I will see your this demo programs and these programs in the site, and
Yes.
I will check it.
Okay, sounds good.
Yeah. Thank you.
Yeah, thank you. Okay, any other questions?
Any other? Let me check. Okay, I don't think there's any other question.
Afternoon session. So what kind of tools we are operating in afternoon session? It's like a MATLAB programming or in
there are 2 lab sessions assigned you to do. I hope you guys can do the reading and come up with scientific literature review report. If you guys need more time working on lab session 1, that's fine. If you want to submit that to Professor Rao later, even I don't know how much extension I should give you guys. Probably Professor Rao can help me to decide that for that short report. But for the afternoon, I would like you guys to work in group, but no more than 3 people in a group. You can have 2-3 people in a group working on a MATLAB session, spend time discussing together, come up with some results. We can take a look. I'll be very happy to grade them after you submit to Professor Rao and give you guys comments. Even the class ends tomorrow. And I just think the afternoon will be a good time for you guys to spend time in groups, and Professor Rao will be there to moderate that. Yeah, most of the time it's MATLAB. It's a EDOS is a MATLAB program, and everything can be in MATLAB. Yes.
Yeah. Okay.
Yeah. Sounds good.
So I don't think there's any other question from the online audience too.
Okay.
Okay.
Very good.
Yeah. We'll wind up now. Is that?
Yeah. So let's adjourn here. And good luck with your lab session. Thank you, Niraj, for helping me out on the afternoon session. So we'll see each other on tomorrow at 10:30, and don't forget if you can prepare for something you are interested, we can have some open discussion at the end of the GIAN course tomorrow. If not, I can keep talking for another 2 hours. That's not a problem. But I talk for 1 hour, 30 minutes, so we can have 30 minutes discussion. I think that would be beneficial, as I said.
Yeah, that will be perfect.
Yeah.
So,
Okay.
yeah.
Very good. With that, see you guys tomorrow. Good luck with your lab. And see you.
Okay, okay.
Yeah. Yeah. Bye bye.